If you studied physics in the latter half of the 20th century, there is one textbook that likely kept you awake at night. Igor Evgenyevich Irodov's Problems in General Physics originated in the lecture halls of Moscow. It contains nearly 2,000 questions requiring a level of analytical rigor that filters out anyone trying to simply memorize formulas. Look at problem 1.80. We have a prism accelerating to the left and a small bar placed on it. We need to find the maximum horizontal acceleration where the bar stays perfectly still relative to the prism. You cannot guess your way through this. We are going to build the exact formula for that maximum acceleration by visualizing the physical reality of the objects. By mastering this specific setup, you learn how to construct accurate free body diagrams for any complex multi-body system. This diagram shows the starting point. Tracking forces while the system moves left requires complex vector tracking. Step 1. Change our perspective. We lock our view directly onto the prism. Now it is stationary. In this non-inertial frame, we apply a fictitious force. The prism accelerates left, so this pushes the bar right with a magnitude of mw. Next, we add mass times gravity, mg, pulling down. By shifting our frame of reference, we have taken a dynamic, moving system and turned it into a static equilibrium problem. Now we have to determine the friction. This is where many students make an error in their diagrams. It is tempting to rely on the basic rule that friction always points up the ramp to stop an object from sliding down. But remember our condition. The prism accelerates left at its maximum value. That immense horizontal pseudo-force drives the block right. Without friction, it would slide up. To keep the block stationary, static friction must actively fight that upward motion. Therefore, our friction vector points down the ramp. You have to visualize the physical limits of the system. Memorization fails. Logical deduction gives you the correct vectors. Step 2. Establishing our coordinate system. We align our axes with the ramp's surface to evaluate forces pressing directly into it. We take our gravity vector and find its perpendicular component, giving us mg cosine alpha, pushing down into the surface. Often, this is where the normal force calculation stops. But our pseudo-force is horizontal, so a portion presses directly into the ramp. We split it, mw sine alpha. The true normal force is the sum, mg cosine alpha plus mw sine alpha. Horizontal acceleration pushes the block harder into the ramp, increasing the total normal force. This directly increases the maximum grip of static friction. Step 3. Balance the parallel forces. Upward forces must equal downward forces. Pushing up is our pseudo-force component, mw cosine alpha. Pulling down is gravity's component, mg sine alpha, plus static friction. We set them equal, cancel the mass, and isolate w to find our maximum acceleration formula. Notice the denominator. Irodov's rule ensures it remains positive. If k were larger than that limit, the friction would be so powerful that no amount of horizontal acceleration could ever force the block up. The math accurately reflects the physical boundary. We have our formula. By carefully unpacking the forces, the algebra falls cleanly into place. This required 3 specific deductions: shifting into a non-inertial frame, verifying the direction of static friction, and calculating a normal force that includes horizontal acceleration. Correctly solving advanced mechanics requires building an accurate physical model first. The math is just a translation of your diagram. When you face your next problem, don't start with the equations. Set your reference frame, trace the physical limits of the objects, and draw the reality.